Hello again. This is a short but unpleasant part of the unit where we get into melting and boiling points and intermolecular forces. Let's try to survive it together. What does the boiling point of a substance indicate about its intermolecular forces? When you have, let's say we have a solid, so we have a bunch of molecules, and if they're in solid form, that means they're in some kind of crystal, so they're arranged in a fairly orderly fashion like this, all sticking to each other and not a lot of movement. They're vibrating, unless they're at absolute zero. They jiggle around a bit, but there's not a lot of motion. So the heat that these particles have is the vibration that's trying to rattle them apart and make them go flying. The heat is trying to make them scatter and move. And a fight is going on here between the heat that wants to make them scatter and move and their intermolecular forces that are trying to hold them together, that want to make them just hold and sit still. There's a constant fight going on in every material between the heat trying to make it melt and vaporize and the intermolecular forces that are trying to hold it together. If it's a solid, that means the intermolecular forces are definitely winning. The object's just holding its shape and sitting there. If it's a liquid, it's kind of a tie. The heat and the intermolecular forces are kind of equally strong. And if it's a gas, that means heat is winning. It means heat has torn this substance apart into a bunch of loose particles and they're bouncing all over the place. It means the intermolecular forces weren't strong enough to hold it together. So if something has a high boiling point, something like steel that takes a lot of heat to melt, that means it has really strong internal forces holding the particles together. If something has a low boiling point, like air, which even at room temperature is a gas, that means there isn't much force holding it together. It only takes a little bit of heat to vaporize it. So stronger forces mean a high boiling point, weak forces mean a low boiling point. For this, list these molecules from lowest to highest boiling point. These questions are usually a bit miserable. Start with what forces they have. Everything has London dispersion. This has London dispersion, that has London dispersion, that has London dispersion, and that has London dispersion. Which of these are polar? CH4 is a tetrahedron. It's symmetric, so it's not polar. C12H22O11, I happen to know this is like a pentagon stuck onto a hexagon. It's not symmetric, so it should have some polar forces. It should have some dipole-dipole. How are you supposed to know that? Hard to say. You'd have to search for this shape. This is why these questions annoy me, because they require a lot of insider knowledge. But this is sucrose. It's table sugar, and you can search up its shape if you're curious. H2 is perfectly symmetric. It's an H attached to another H, so no dipole-dipole force. This is asymmetric. It has dipole-dipole, and so does this. That's chloroethane. And which of these have hydrogen bonding? This does. I know because I've seen it. This doesn't have NO or F. This has an H attached to an O, so that would have hydrogen bonding. And this has a hydrogen and a chlorine. That's not good enough. We need NO or F, so no hydrogen bonding there either. So the ones with the lowest boiling points should be the ones that have the fewest forces. Hydrogen and methane should have our lowest boiling points because they only have London dispersion force. Between these two, which one's lower? Well, remember, London dispersion force scales with how many protons and electrons you have. Hydrogens have one each, so there's a total of 2 here. Carbon has 6 protons, and each carbon has 1, so 10 there. Methane has 5 times as many charged particles, so it should have 5 times as much London dispersion force. So it should have higher boiling point because of that. So that takes care of the ones with just London dispersion force. Do we have any ones with just 2 forces? Yep, C2H5Cl should be in the middle. It's the only one that has London and dipole-dipole, but not hydrogen bonding. And between these two, well, they both have all 3 forces, so that's problematic. This one has a hydrogen bond, and does sucrose have multiple hydrogen bonds? I think it does. I just Googled sucrose molecule and I'm looking at it. Yeah, it's got 1, 2, actually it has a ton. I feel bad not knowing that, but the actual number is 1, 2, 3, 4, 5, 6, 7, 8. Yeah, if you search the sucrose molecule, you'll find it has 8 hydrogen bonds in it, which is the strongest kind of bond. So that should mean that sucrose has the highest melting point of all of these. Another minor cheat you can use if you know most of these substances, hydrogen is a gas, so that should tell you it has weak intermolecular forces. Methane is natural gas, gas again. You probably don't have any experience with chloroethane, I know I don't. But then we have ethanol, this is the alcohol people drink, and this is sucrose. So ethanol is a liquid, we know that from experience, and sucrose is a solid. So if it's a solid, it must have the strongest intermolecular forces. That tells us this one must have the highest boiling point. So some of this comes from deduction from the numbers of forces that it has, and a little bit of it comes from recognizing certain chemical names and knowing what those can tell you. Predict and explain the relative boiling points of fluorine and HCl. So what's tricky with this is they both have London dispersion force, and fluorines have 9 protons each, so there's a total of 18 protons here. Hydrogen has 1 proton and chlorine has 17, so this also has 18 protons. So they should be really, really close on London dispersion force. That's no help. So what else is different about them? Is fluorine polar? It better not be. It's 2 identical fluorine atoms. Their electrons should be shared dead center between them. So fluorine is perfectly nonpolar, but HCl is polar. This is 2.2 versus 3.2. Significant difference, which means HCl has dipole-dipole force, which means it should have a higher boiling point than F2. When they say relative boiling point, that means we know you can't tell us the actual number, that's university stuff, but at least tell us which one is higher. Okay. Another thing we can get from knowing these forces is the solubility of a substance. And briefly, the rule is polar stuff dissolves in other non-polar stuff, and non-polar things dissolve in other non-polar things. A lot of people know the rule that oil and water don't mix. And the reason for that is that water is highly polar, pretty significant bond dipoles between oxygen and hydrogen, and oil tends to be alkanes and alkenes, the occasional alkyne, and that makes it pretty much nonpolar. And so when you try to mix an oil and water, you get a nonpolar substance and a polar substance, and they don't want to combine. But if you put a polar thing in water, it dissolves very well, and if you put a nonpolar thing in oil, it dissolves very well. So like dissolves like is the simplest rule. So when they say which of the following would be soluble in water, what they're really asking is which of the following are polar. Sorry, bad framing there. Which of the following things are polar? C2H5OH, there's only 1 oxygen, it's on the far right end, so this should be polar. C25H52 is an alkane. It's very symmetric. It's a long chain of, it goes CH3, CH2, 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 CH2 for a long time, and then CH3 on the end. Very symmetric, therefore nonpolar. NaCl we've seen as an example. We know that's polar. And C5H12 is pentane, again, an alkane, nonpolar, because it's nice and symmetric. So we would expect C2H5OH and NaCl to dissolve well in water. These other two are, this is like a wax and this is like an oil. They would not dissolve in water. Now, same question, which of the following would you expect to be soluble in hexane? Hexane is C6H14. It's nonpolar. So soluble in hexane is equivalent to saying nonpolar. So pretty much the same question as 339, except now they're asking for find the nonpolar ones instead of find the polar ones. So for this, methane is an alkane, so it's nonpolar. That should dissolve in hexane. C3H8 is propane. That should be fine. That's another alkane. H2O is water, very polar, so nope, that won't dissolve in hexane. C2H6 is ethane. Sorry, that was harder than it should have been. Ethane is an alkane, so that should be fine. And NaCl is highly polar because large difference in electronegativity, so no. And the answer says, yeah, find the three nonpolar ones, and those are the ones that will dissolve in hexane. And finally, they bring up the terms saturated and unsaturated. When you have a chain of carbons, you've seen we normally assume that every one of those carbons is holding as much hydrogen as it can. Every carbon has 4 arms. If you're using every arm that you have free to hold hydrogen, then we say that you are saturated. Saturated only applies to organic compounds, and it means you've got hydrogen everywhere that you can around your carbons. No empty spaces. Now, if we were to turn this into an alkene, if we were to put in a double bond somewhere, what would we have to do? If I want to put a double bond here, let's say, well, I'm telling these two carbons, I want you to hold hands one more time, and to do that, each of them would have to, oops, that didn't work the way I wanted, sorry. Each of these carbons would have to release one of the hydrogens that it's holding. It would have to free up a hand. And now that it's done that, now those carbons can hold hands twice. And when you make a double bond like this, there's a space here that could be holding a hydrogen, but it isn't. There's a space here that should be holding a hydrogen, but it isn't. So when you've seen a bunch of these molecules, you see these, you notice these gaps and you think, oh, it lost a couple hydrogens there. If you've got missing hydrogen, we call you unsaturated. So basically any double bonds between carbons or any triple bonds between carbons mean a compound is going to be unsaturated. It means if only you two would let go of each other and free up those two hands, you could hold more hydrogen now. As long as you don't do that, you are unsaturated. When you're completely full of hydrogen, then we call you saturated. Make sense? I hope. Let us know if it doesn't.